Make this screencast about some transport mechanisms, specifically diffusion and facilitated diffusion. I will address the osmosis part in a separate one. So again, our text references are here, and in order to understand this, you have to have a solid foundation of what a phospholipid is, and then the structure of the membrane. So these are things for you to review. We're going to focus here on describing and explaining first molecules that are crossing membranes via diffusion and facilitated diffusion, which means then we also have to then be discussing, describing, explaining diffusion and facilitated diffusion. And again, I'll address osmosis in a separate one, even though the slides are here on this PowerPoint. So some basic definitions. Passive transport up here does not require the input of metabolic energy. This is going to just naturally happen. There's a natural tendency for this to happen. So diffusion is the net random movement of molecules from an area of high concentration to an area of low concentration until, I'm going to add this on the end here, until a dynamic equilibrium is established. Dynamic equilibrium is established. So if we look at the images on the left here, we have an area of molecules that is concentrated. Right? So this is a concentrated. And what we say is that there is a difference across this membrane. Now, you don't need a membrane in order to have diffusion. But in this example, we do have a membrane, and typically in biology, we're dealing most often with things crossing membranes. But this membrane is said to then be permeable to these solutes, right, that are dissolved, and the solute being each of these orange dots up here. So these orange dots are concentrated on one side of the membrane up here, and on the other side of the membrane, they are not concentrated. So we say that this can also be described as there being a difference across the membrane. There's a difference across the membrane. And the tendency will be for those solutes in that solution that are moving randomly, as all molecules are, in continuous movement. As they are moving randomly, the tendency will be for them to then diffuse, tendency to diffuse. Now, as long as this membrane is permeable, these molecules are going to diffuse from an area of higher concentration to an area of lower concentration until down here there's a dynamic equilibrium. Now, it's difficult to show this dynamic equilibrium on a static slide, but there is an animation that's posted on Blackboard that will sort of show this to you animated wise. But what we mean is that for every molecule that moves to this side of the membrane, there will be another molecule that moves to that side of the membrane. Right? And we have this dynamic equilibrium down here established where now there's equal concentrations on both sides of that membrane. The right side of this diagram over here, again, sets up where we have a difference in these solutes across the membrane. And the important part about this is that I have, we'll call these solutes A and these solutes B, and that solute A, the concentration gradient favors, the gradient, we say, favors diffusion down. And then B, we say that the gradient favors diffusion up. And I'm using up and down as they pertain to the slide here, right? So the tendency will be for A to diffuse down and for B to diffuse up, again, from areas of lower concentration to higher concentration. The important thing about this is that the movement of A is, let's start this again, A is independent of B. So the tendency for the A molecules to move to an area of lower concentration is independent of the tendency of the B solutes to move to an area of lower concentration. Meaning that just because an A comes down doesn't mean that a B is not going to go up. Just because an A moves down does not mean that a B is not going to go up, and vice versa. Okay. Now, again, this is assuming that the membrane here is permeable. Right? So let's take another look at this concept on another slide here. And the title here is similar. Passive transport plays a primary role in the import of resources and the export of wastes. So I want to call your attention to the fact that transporting things across membranes, you can go either way. You can get things in, or you can get things out, and or you can get them out. So just because the diagram here is showing these solutes moving into the cell, right, or this way of the membrane, doesn't mean that they also can't go the opposite way. So at the top of this diagram here, we're showing, again, this passive diffusion, where these molecules are in high concentration on one side of the cell, on a lower concentration on the other side of the cell membrane, and the molecules are diffusing simply right across that membrane. Now, as you know from your membrane studies here, that these molecules, since they are able to freely diffuse across, are small, uncharged, and or non-polar, right? Non-polar, uncharged, small. Pretty much the examples we see most often in biology would be things like CO2 and oxygen gas. These are really the only two things that you would be considering going across the membranes relatively easily. Everything else, right, is represented here by this this triangle right here, and we say that most things are going to be large, have some sort of charge to them, right, or will be polar. So large charged polar things will need to get across membranes. However, they don't just simply passively diffuse across. They are going to need some sort of protein channel or protein carrier. So protein channel or a carrier. And this protein channel, this protein carrier, is often sometimes referred to as a pore. Right? These protein carriers or channels, these pores, tend to be specific. So they show specificity, meaning that they are, you will have channels for sodium ions, say, and you will have channels for potassium ions, and a potassium ion wouldn't go through a sodium channel and vice versa. And these channels and these carriers also, as proteins, have the ability to change their conformation. So these two aspects down here help to describe the membrane, or most membranes, as being selectively permeable. You may also hear it referred to as semi-permeable. Selectively permeable is a little bit more descriptive because you're getting specific things going across there. Regardless of whether you're dealing with a channel or a carrier here, this is still a diffusion mechanism, meaning that these large charged polar things are going to be going down their concentration gradient, randomly moving down a gradient from areas of high concentration to areas of low concentration. This diffusion, still referring to going from high to low concentration. Again, brackets around something mean concentration of. So you're going from an area of high concentration to an area of low concentration. Right? This is the diffusion part of this definition, right? But the facilitated part of this definition is having to do with these proteins right here. Right? These proteins help get help get those large charged polar molecules across the membrane. And again, either in or out, either direction. But as long as that direction is from high to low, you are dealing with a diffusion situation here. Okay, so these two animation buttons right here and right here, I don't think work on the screencast, but the URLs are posted on Blackboard underneath where I posted this screencast. So facilitated diffusion, and and diffusion. The rest of this deals with osmosis, which again I said I will address in a separate screencast. So I'm just going to stop this, keep all that, and